Dear students, having discussed the logic of hypothesis testing, we now consider the two approaches to hypothesis testing. One is the critical value approach. The other one is the p-value approach. Critical value approach to hypothesis testing and the p-value approach to hypothesis testing. In this session, we discuss the critical value approach to hypothesis testing. Now, with the critical value approach, we choose a cutoff point or cutoff points based on the significance level of the test, alpha. We decide a cutoff point based on the level of significance alpha. And the decision to reject H0 involves a comparison of the value of the test statistics with the cutoff points. A comparison of the value of the test statistics with the cutoff points. Remember this. If the level of significance alpha is 5%, 5%, from the table you will get the critical Z values as minus 1.96 plus 1.96. This is 2.5%. This is 2.5%. And this is the 95%. The cutoff points are minus 1.96 and plus 1.96. 95%. If the cutoff points are minus or plus 2, it is 95.44%. Usually, we consider the level of significance alpha as 1%, 5%, 10%, etc. So, I take alpha at 5%. Then the cutoff points of the test statistics are minus 1.96 and plus 1.96. So, we take a decision on the basis of the value of the test statistics obtained from the sample compared to these cutoff points. That is critical values, critical Z values, which divide acceptance region from the rejection region. Now, as an example to this, we consider an example. Jack tells Gilles that his average drive of a golf ball is 275 yards. 275 yards. That is average drive of a golf ball. 275 yards. And Gilles is skeptical and asks Jack to hit 25 times. Hit the golf ball 25 times. And these 25, the length of these 25 drives are noted. And X bar is 264.4 yards. to 64.4 yards. 25 samples are generated. X bar is 264.4 yards. Now the question is, at 5% significance level, at alpha equal to 5%, do the data provide sufficient evidence to conclude that the mean driving distance is less than 275 yards? Less than 275 yards. Now, to test this hypothesis using the critical value approach, we assume that the driving distances are normally distributed with a population standard deviation sigma is equal to 20 yards. Sigma is equal to 20 yards. The distances are normally distributed. Now, the null hypothesis is H0, mu is equal to 275 yards. H1 is mu is less than 275 yards. H0 mu 275, H1 mu less than 275 yards. If H0 is true, then the mean driving distance is 275. And we will say that the mean driving distance is approximately 275. We will not say it is equal to 275 because we cannot expect that the actual value obtained will be 275 because of sampling error. So we say approximately 275 if the null hypothesis is accepted. That is, mu is equal to 275. Now, to test this hypothesis, what we require is a knowledge of the sampling distribution of the sample mean and also the specified significance level. Now, sampling distribution of the sample mean. As population is assumed to be normally distributed, the distribution of the sample mean is also normally distributed with mu of x bar is equal to mu, an unknown quantity, sigma of x bar is equal to sigma by root n is equal to 20 by 20 is the population standard deviation. Root 25 is equal to 4 yards and x bar is normally distributed. X bar is normally distributed. Alpha is 5%, sigma 20, the hypothesis. Then Z is x bar minus mu of x bar divided by sigma of x bar is equal to x bar minus mu, because mu of x bar is equal to mu by sigma of by root n. This is equal to x bar minus 275 divided by 4. X bar minus 275 by 4. And the value is equal to 264.4 minus 275 by 4, and it is equal to minus 2.65. Minus 2.65. That is the critical value. Now, this is a one-tailed test because the null hypothesis is mu less than 275. So, the 5% critical value is in the left tail of Z. 5% here, 0.05. And this is 95%. If it is a two-tailed test, 2.5 here, 2.5 here. Right-tailed, 5% here. Now, the the 5%, so 95% critical Z is minus 1.645. Minus 1.645. And as we know, the value of Z is equal to minus 265 minus 2.65, not 265, minus 2.65. It is in the critical region. So null hypothesis is rejected. And what we say is the mean distance of jacks is less than 275. The null hypothesis is rejected. And when we reject the null hypothesis, the probability of rejecting a true hypothesis is only 5%. So we can reasonably conclude that null hypothesis is not correct. Suppose that the test statistics was in the acceptance region. We accept H0, but we do not know what is the probability of committing a type 2 error. So we will not say we accept H0. What we say, we do not reject H0, because we do not know whether we are committing a type whether we are accepting a false hypothesis or not. On the basis of evidence, we cannot reject H0. Now in this case, H0 is rejected because the value of the test statistics is in the rejection region. And as I told you earlier, if you want to conduct this test in terms of x bar, the distribution of x bar is like this. This is 260, 275, this value, and 275 here. This value is 268 point something, can be calculated. So, but we will not use the estimator and its sampling distribution directly for hypothesis testing. What we use is the test statistics. The test statistics for hypothesis testing. Now, in the context of critical value approach, the set of values of the test statistics resulting in the rejection of H0 is known as the rejection region. That is, the values of the test statistics which results in the rejection of H0 is the rejection region. And values of the test statistics not results in the rejection is known as the acceptance region. Acceptance region. And the value of the test statistics which divide a rejection region from acceptance region is known as the critical value. In this example, it is minus 1.645. And this terminology is applicable to all hypothesis testing procedures. Critical region, acceptance region, and critical value. And we generalize this procedure like this. If we have a two-tailed test, then the value of the test statistics is Z, and depending on alpha, let it be alpha is equal to 5%. Then these two are the rejection regions. This is the acceptance region. That is, do not reject H0. Reject H0 if the value of the test statistics is in this region. Otherwise, reject it. And it is a two-tailed test. And then if the null alternative hypothesis is less than type, then we have left-tailed test, rejection region, acceptance region, 5% in the left tail only. Then this is the rejection region, 5% in the right tail only. So whether you conduct a two-tailed test, left-tailed test or right-tailed test depends on how you specify the alternative hypothesis. How you specify the alternative hypothesis. And rejection region and acceptance region depends on the value of alpha, the level of significance. If alpha is 5%, this. If alpha is 10%, it will come here. If it is less than 5%, it will be extended like this. Now, let us see how we obtain the critical values. Now, obtaining the critical values is very simple. The procedure is once in the form of steps. Let me write these steps as it is convenient to write the steps like this. We assume that the variable under consideration is normally distributed. We assume that population standard deviation is known. We assume that, also remember this, even if population is not normally distributed, if sample size is greater than 30, using central limit theorem, you can again use the fact that this test, the sampling distribution is normal. So H0 is mu is equal to mu 0. Then Z is equal to x bar minus mu 0 by sigma by root n, the test statistics. And if alpha is 0.05, for a two-tailed test, remember this, the critical values are plus 1.96 minus 1.96. For left tail, 5% in the left only, it is minus 1.645. For a right tailed test again, minus 1.645. Like that. This is the procedure. So you formulate H0 and H1. You decide the level of significance, compute the value of the test statistics, determine the critical values. If the value of the test statistics is in the critical region, reject H0. Otherwise, do not reject H0. That is the critical value approach to hypothesis testing.